Okay, great. So yeah, thank you so much. I'm really happy to be here talking about working with R from the command line. So my name is James Lamb. I'm an engineer at a company called Saturn Cloud, where I'm doing no R at all during the day. I'm mostly working on Python. But I'm also a maintainer on an open source machine learning project called lightgbm, where one of my main responsibilities is working on the R package. So I still work on R stuff, on nights and weekends in open source time. And I have found myself writing a number of R scripts that are only intended to be used from the command line, that are never intended to be kind of run interactively in an IDE or anything like that. So I've been kicking around this idea of this little talk for some of the things I've learned about that process for a little while, and I'm really happy to be here to share it with you for the first time. Okay, great. So the way that I've structured this talk, first I want to very briefly explain just a few concepts that are important to know generically about, running programs from the command line, whether they are written in R or whatever. After that, I'm going to walk you through every argument to the Rscript executable, and I'll explain what the Rscript executable is if you're not familiar with that. And then finally, we'll walk through kind of step-by-step building a small command line tool in R. This will be a tool that lints R code with Jim Hester's lintr package. I should also say at this point, if I can escape, all of the code for this talk is available, on my GitHub. If you go to github.com/jameslamb/talks, it's released with a permissive open source license. You can do whatever you want with it. You can start a company out of this code if you want. And you can also try these. I've kind of written out each of these examples, so you can try them later if you'd like. Okay. So from this point, let's go back to some slides. Okay, so the first thing to know about running any programs are these important things called input and output streams. And there are three of them that are really important. One is called standard in. Standard in is kind of the way that you pass data into a program. And when I say pass data into a program, this is different than maybe reading in files. You work with many programs in R or other languages that read files, that go out and ask for data from a web service, from a database, something like that. That's not exactly what I'm talking about here. This is literally data that's provided by the calling environment to a program when that program is first invoked. And I'll show you some examples of that. And then programs have two different output streams, standard out and standard air. The names give you a sense of their kind of intended use, but they're really just two different things, and I've seen many different uses of them. So to give you an example, and we'll talk about this in a second, if you load up an R package, and you know what, let's actually just do this. Why make this theoretical? If you load up an R package that masks a bunch of other packages stuff, like our friend's dplyr, which I don't have. Great. Oh, I am definitely not installing that right now. Let's try data table. Okay, perfect. If you library up data table, you're going to see all this stuff that's printed in red, right? Well, this isn't an error. Like, nothing went wrong. This is just the usual, I'm loading an R package, startup message type of stuff. If you were to do this at the command line, all this stuff in red is actually written to this output stream called standard air. And so then all that it means is basically there are these streams that are used to separate kind of the diagnostic information that is maybe like the main output of the program, and other things that are, say, like warnings, errors, like kind of information about running the program, but not its primary output. If that's confusing, don't worry. We're going to go through a bunch of examples. When you work with programs from the command line, you can take these input and output streams and redirect them around. So in this example, I have a file called readme.md. And what I'm doing is I'm saying, okay, take that contents of that file, it's just a text file, treat that as the standard in to this process called cat. Cat then just takes the data that it gets on standard in and pushes that data back out to its standard out. And this pipe operator is saying, okay, take this process as standard out and make it the standard in of the next process. And then I'm passing it to this other program called grep that's taking in the contents of this file as its standard in, doing some stuff, and then pushing its standard out to a file. So this is like a little bit overcomplicated and contrived just to prove the point. But this is an example of kind of moving data around in these streams. And what this little program produces is only basically all of the section headings from this markdown file, only the things that begin with a hash. And if you want to learn more about kind of some of these command line tools that I'm using, if you're not familiar with the Unix command line tools, there is this really interesting blog post from 2014 that's called Command Line Tools Can Be Faster Than Your Hadoop Cluster that I recommend that you take a look at. But this talk is not about that at all. Okay, output streams. Congratulations, we've all mastered one concept of writing command line programs. The second concept that I want to talk about are exit codes. So when you run a program in any operating system, that program is going to, more precisely, that process is going to, when it ends, exit with what's called an exit code. And the meanings of these exit codes are a little bit different as you get into different systems and different types of stuff, but you can basically rely on the fact that if a process returns an exit code that is anything other than the number 0, then that process is going to be considered failed. And there's a reason that I say failed, sort of. So think about if you've ever written, say, unit tests for a library or something like that, right? Many unit testing frameworks, if they detect any failing tests, they're going to return a non-zero exit code. They'll return 1 or 127 or something like that. And that doesn't mean that the program failed when you run those tests, in the sense that, you know, something went differently than you expected. The code all actually did exactly what you expected, right? Your tests were run and the testing framework looked at your code and said, nope, something like one of these tests is broken. But that non-zero exit code is a way for processes to indicate to the things that called them into the operating system that, hey, this didn't, not everything went perfect and there's something that's worthy of your attention. This concept is important because this is how every continuous integration tool works. So if you are working in open source projects and you're using AppVeyor, Azure DevOps pipelines, GitHub Actions, Travis, Circle CI, Jenkins, all of these different things, it can kind of seem like magic at first. It can seem like I move all this stuff around in this YAML file. Like I read this blog post that said I'm supposed to call this command. I don't really understand what's happening. But at the lowest level, in all of these continuous integration tools, all that's happening is you organize a set of processes to be run one after another. And if any of the processes exits with a code other than 0, your build is considered failed. And once you kind of get used to that, you can also get really creative with what you consider to be a part of your build. So you can kind of get out of the idea of just maybe running unit tests and linters, and you can write your own custom code that like checks if, I don't know, anyone used the internal secret code name of a project in an open source repo or something like that. Okay, beautiful. Input streams, output streams, exit codes. Now let's go look at some examples with Rscript. And for this point, yeah, we're still going to do a little bit of a mix of slides and terminal. So what is Rscript? If you have R installed, you have Rscript installed. So Rscript executable is bundled with every installation of R. And the Rscript executable is used, it's intended for running R code from the command line. So when you run R, right, if you run R with no arguments, you're going to get a REPL, right, a read eval print loop, where I can just like write interactive code and do whatever. That's not the purpose of Rscript. For Rscript, excuse me, for Rscript, the purpose is to run R code that's either passed in as a string or that's stored in a file. And so this is more for the use where you're using R, maybe in a system. I actually have a couple, a list of these. You may use this when you are working with R in an environment where you don't have a GUI, a graphical user interface, or you don't have a screen in front of you. And that's like maybe if you are remoted into some server, like a virtual machine from a cloud provider, Maybe you're writing some code to be run on one of those continuous integration services, something like that. Maybe you're running some R code in the process of building a container image, something like that. When you use Rscript, this also means that the output of your programs can be chained together with other programs. So, for example, we could do something like print hello, print goodbye, and then maybe pipe that to some other program and say filter out everything that wasn't good. And then we're only going to get the line goodbye, even though we also have a hello being printed there. Something like that, right? It's kind of a trivial example, but Rscript allows you to kind of chain together your R code with maybe some other programs. And then finally, one use that I have for Rscript a lot is running something where you want to direct the output to a file. And so it's kind of, I could, for example, do something like this. Hello, and write to a file. And now my stuff is in a file. And maybe for one line of code, that doesn't really matter, right? It's printed hello. But if you were maybe generating random data and you wanted to just write it out to a CSV or do something like that, you might find that it's a little bit more lightweight, a little bit easier experience to do that from Rscript, have it write to a file and kind of go on with your day, rather than tying up the console, the console in your RStudio or something like that. So that's the basic idea with the Rscript executable. And I actually have an example of this. So I have, okay, beautiful. So I've actually written some example code for the purposes of this talk, and it's all available in the repo. And so, for example, you can see I've written this little script that, and I'll zoom this up so people can see, that just prints 10 random numbers and just tells you that it's doing that. And so if you have code like this that's sitting in a file, with Rscript, we can just run that directly from the command line. So I can just run sample script sample print, and that little code's going to run and print some random numbers to the console. We're going to talk through a bunch more examples of this. Okay, one thing that you'll see me use a lot in these examples is I think the single argument to Rscript, which is technically an argument to R, and that is -e. This actually has a typo. Let's just fix it right now. So when you run Rscript -e, -e says, I'm not going to give you a path to a file with R code. I'm going to just give you some R code that's jammed into a string. So for example, I'm going to library up data table and run a little data table code. And let's take a look at that. And kind of like you'd expect, right? A little data table object was created and printed. So Rscript -e, I use this all the time to test things without having to spin up a REPL. So for example, if I am maybe checking whether a package is installed on a system or something like that, I find that it's easier to just do so we saw that dplyr isn't installed on my system, right? I find that it's easier to just do Rscript -e, library, whatever, just to check, rather than, either starting up RStudio or running R or checking that way. Just a personal preference. Okay. Beautiful. So I talked a minute ago about these concepts of standard error and standard out, right? There are a couple of main kind of base R functions that you can use for producing output. And some of these print a standard out, some of these print a standard error. And that's why you might see different colors in a terminal, like in RStudio, for example, from these different types of outputs. So I am going to prove to you that prints to standard out by default, and that the functions message, warning, and stop print to this other output stream called standard error. So what I am doing here, where's my little, sorry, one second. Maybe I need to refresh the page. This is what happens when you push changes to your talk 2 minutes before you give the talk. That's okay. We're just going to run it like this. So what you can see, right, I'm going to run a print and a message And I think that's kind of enough to prove the point here. And what I'm going to do is something that's called redirection. So I'm going to take the standard out of this process, which is referred to with the number 1, and write it to a file called standardout.txt. I'm going to take the standard, let me make this a little larger. I'm going to take the standard error of this process and write it to another file called standard error. And what we should see is that the stuff that got printed is in this file standardout.txt, and the stuff that got messaged is in standard error. Let's see if that's true. Okay, it looks like the standard error thing worked as expected. And it looked like the standard error thing worked, right? So this is kind of an example of how from within R, different code that you run might be printing to different versions of these output streams. Now, when you're working with R in the console, or you're working in another REPL, you don't necessarily really care, right? Because these output streams, for the most part, they're kind of all blended together. You just see a bunch of messages. And yeah, maybe some of them are a different color, but like whatever, who cares? They're all there, right? This does start to matter a lot when you work in systems that, for example, are running your code somewhere and then taking the standard error and standard output and shuffling it off to a system that stores logs. So if you're running like a Shiny app or a little deployed machine learning model or something, it might matter a lot whether your code is writing to standard out or standard error, because that's going to determine maybe how that system that is aggregating and storing your logs, how it stores it and where it puts it, as an example. Okay. As promised, the next thing that I want to talk through is each of the arguments to the Rscript executable. And I think this part might actually be a little bit easier in slide 4. So first, you can use the flag help, just like in many other command line interfaces outside of R, to print all of this documentation that describes what Rscript does. And it's going to tell you how to use Rscript. It's going to tell you some of the options. Excuse me. And then importantly, it says here that you can basically pass any options to R, and only the ones here are the ones that are most commonly used with Rscript. So you'll notice, for example, this -e that I talked about is not actually in this list, right? So I like to use the Rscript executable for stuff where I'm not running interactive code, just because I think it's a little clearer. But most of what I've done, you can also just run with plain old R. And you can see that with help. Okay. -- version does exactly the thing that you would expect. It prints the version. If you ever need kind of more, if you ever need tighter programmatic access to the version in R, there are functions built into R to get the major version, the minor version, the release name, all of that stuff. But this will just give you a general diagnostic piece of information like, hey, what version of R do I have? -- verbose is going to say, hey, Rscript, I want you to tell me more about exactly what you're doing. And so in this case, you can see with running -- verbose on my Mac, that's why you see this -library thing. Rscript actually told me exactly where it found R and all of the arguments that it passed. Kind of cool. -- default packages. This is a cool one. So when you run code in R and you haven't run any library statements, in most distributions of R, a handful of packages are going to be loaded. Packages like tools, stats, graphics, methods in some situations and not in other situations, things like that. But you can, from the Rscript executable, actually configure that set of packages. So what you can see here is I've tried to run a little code that creates a data.table. And the first time I ran it, I got this error that said, could not find function data.table, right? And that's because I haven't libraried up that package. That's not one of R's default packages. Passing this flag before any of the code in either the file that you pass or the string that you pass is executed, R is going to attach all of the packages you give in this comma delimited list. So it can be kind of nice. Okay, save and restore. So when you work in R, maybe you've had this experience in RStudio or the R REPL where you go to quit your session and you get maybe a pop-up or an interactive prompt that says, would you like to save this session's data or something like that? And if you select yes, then all of the current state of the global environment is going to be stored in a .r data file. Well, that is exactly what the --save command does. So --save, the --save argument. Passing --save says, hey, take the output of running this, and before you kind of close down the R session, save the state of the global environment into a .r data file. And so here I've run a little bit of code that creates a variable called sumVar. When I try to run a new bit of code that prints the value of that, R is going to say, I don't know what sumVar is, right? Because I passed no restore, R is going to say, look, I'm in a clean session, not really sure what you want me to do here. I don't know what sumVar is. Passing --restore is going to tell Rscript, oh, if there's one of these .r data files laying around, I want you to pick up that file and kind of recreate my global environment from that file before running my code. And then just this small statement print sumVar is going to work because that value of sumVar is saved in the environment. There are a lot of different ways to configure how R runs in your environment. There are these files called .rprofile, renviron, probably other files that I don't know about, that all are sourced in like what I would consider a fairly complex hierarchy of decisions that R makes about the state of your environment before it runs your code. And this image was attached to this tweet from Thomas Peterson. I really like it. I know it's hard to see. It's kind of the point that it's hard to see. There's so much stuff there that it can't easily be represented. These flags to Rscript, like no site file, no init file, no environ, these give you control over these different types of config files, and they allow you to ignore them. So to basically say, I want to be very sure that the code that I'm running here isn't affected by any of these configurations that might be different as I go across different environments. Like maybe you're distributing a script that you expect contributors to your library to run locally, and you don't want to deal with the differences between their kind of local rprofile files against each of their laptops, something like that. Finally, keep this picture in mind. I want to show you my favorite Rscript argument, and that is --vanilla. --vanilla says, what you see is what you get. It says, don't silently reload my environment from this dot file that happens to be laying around, and don't run any of this code that might be in the various renviron or rprofile files. Just run the code that I told you to run without kind of any of the bells and whistles. So I like to use this defensively when I set up things that I know other people will run, because this will really give you a fairly strong guarantee that just the code that you expect to run is kind of all that gets run. Okay. That is the extent of the Rscript stuff. And then the last thing that I wanted to show you in the 5 minutes or so that we have left is an example of writing a command line program. And I'm going to go through this very fast. But all of this code is available at my GitHub repo, and you can kind of walk through this yourself. So what I want to do is look at a couple examples of writing a script that we can use to lint all of the R code in a directory. So let's look at the first version of this. There it is. Did you see this file wasn't saved? That's why my example wasn't up there. Okay, so let's look at the first version of this. This is a little bit of code with the lintr package. And what this package does is you can specify which of these linters you want to use. A lintr is basically a static analyzer that will look at source code and find problems or things that are worthy of noting. So for example, the assignment lintr will catch if you're using an equal sign instead of the little arrow for assignment, or single quotes kind of does what you think it does. To-do comments will say, hey, you're including some to-do comments in here. Are you sure you want to do that? Unneeded concatenation will catch cases where you have code like this, where you didn't really need to use C because there's kind of implicit, the literal for is already implicitly a vector in R, stuff like that. So we could run this little script, and let's see what it does. Okay, so this does some interesting stuff. It definitely found a couple of problems in my code, but there are a couple ways that we could improve this script. So first, The biggest one is the exit code. If I check the exit code, even though this found some linting errors, this exited with an exit code 0. And so that means if I wanted to use this in a continuous integration environment, I couldn't rely on this script to fail my builds if I detect some of these style problems. So that's no good. Another problem that we have is that the directory that I want to lint is hard-coded into the script. So every time I want to run this script, I'm going to have to change the code to point to a different directory if I want to change directories. So let's look at a little bit better version of this. Here I'm not using any new libraries, but I'm using this base R command called commandArgs. And what commandArgs does is it captures additional arguments that you pass to R or Rscript after all of the arguments that are recognized by R and Rscript. And so in this case, I'm going to be able to run this code passing in a directory to lint. And this way I won't have to change my code in the future if I want to lint another directory. And then what I've also done here is I've captured a list of the linting errors that were found. And I'm using the built-in R function quit to say, hey, explicitly quit this script and set an exit code that is equal to the number of errors. So now I can rely on this to fail. Let's look at this real quickly. Okay, great. So now I can actually pass this a directory, and it still did all my same stuff, but now we got a non-zero exit code. Okay. In the interest of time, let me skip ahead to one more example of this. So now we've got our thing kind of basically working for CI, but it might be a little bit hard to understand as an executable by itself. So I've added a bunch of other fancy stuff. With the argparse package, you can define new command line arguments where instead of having to rely on this like careful ordering of extra strings, you explicitly can have basically keyword arguments. I'm going to be able to do a little bit of help data. With the arguments I'm parsing from argparse, I am going to be able to run a -- version on my code, just like you do with other executables that you install. I'm going to print a little bit of fun ASCII art. And with the package crayon, which I realized I didn't actually library up, with the package crayon, I can actually change the color of the output. So let's take a look at what this looks like. If I run -- help, all of my help documentation from my script is going to be printed. Ooh, ah. If I run -- version, this little bit of, oh, right, duh. It's pretty -- version. This little bit of version information that I've defined is going to be printed. And then finally, I can do this and explicitly pass the directory I want to lint. This is called sample R code. And what you're going to see is now I got my little ASCII art mocking SpongeBob. It's printed in yellow because that's the color that SpongeBob is, followed by all of my linting problems. And then in this case, I have a little bit of code that's saying, hey, print out this end bar saying how many issues you found. If there's any problems, make it red. If it's all okay, make it green. And so I've made it red here. That is actually basically the extent of what I wanted to talk about today. I know that we went through kind of a lot fairly quickly, but all of the information is available on my GitHub. You can take a look. If you are really feeling like you want to get more examples of argparse and crayon and like you really want to go deeper into this, you can go take a look at this other kind of cursed command line script that I wrote in lightgbm, which accomplishes a much more complicated task of building this C++ library plus an R package on top of it on many different types of tool chains, different architectures, using a tool called CMake. So that one is like a lot more complicated. You'll learn a lot more stuff. And then actually the final thing I'd like to say is I only very briefly went over a handful of packages that I find useful in writing command line interfaces. But if you find yourself writing a lot of these scripts that are going to be run either interactively in an environment without a terminal, without a GUI, or maybe that are going to be run in a continuous integration environment, you might consider some of these other great packages. Feel.logger is a very lightweight logger. JSON Lite is great for working with JSON. Opparse does something similar to what argparse does. praise generates random encouraging messages. So you can have your CLI end with like, you did great, you should be proud of yourself. ProcessX is a project you can install from Crayon that has some more powerful mechanisms for running shell commands than what you might find in the built-in, system and system2 commands. And then the progress package is really, really nice. I've only just started working with that over the last few weeks, and that can be used to print progress bars out to the console. So if you have something that's long running, like maybe you're doing a big grid search or a simulation or something, you can actually print out progress bars from your CLIs. And with that, I have already gone 3 minutes over my time, so I will stop talking. Here is my contact information. Please feel free to contact me if you have any questions about this. And yeah, thank you so much for your time.
Thank you. We're experimenting something new this time. We're going to combine a Q&A for both talks. Since we have the same topic today, it will be nice. And thanks, James. Neal, do you want to share the screen?
Yeah, I can take over. Yeah, thanks, James. That was fantastic. And I think it'll go pretty well with my talk. We'll see. All right, are we up? I can't see you. I see mine.
Yes, yes. We can see, we can hear.
Good.
Okay, great. All right, and then we can see top.
Yes.
Okay, cool. I'll go ahead and
your camera's off now.
Oh, shoot. Let's turn that back on. How's that?
Perfect.
Okay, cool. All right, well, I think we got all that worked out. So great. So I'm going to be talking about not the command line specifically, but about the terminal, which is a program on all your computers, whether you knew about it or not, and specifically for what I would call survival strategies when using it. So quick summary of the talk. So I'm an independent consultant. So most of my work is data analysis that happens on other people's computers, other companies' computers. And so I have to follow their data and security policies and governance, et cetera. So I don't get to choose my tools necessarily, and often bare terminal is the only choice I get. But I've been doing this for many years at this point, and there are ways to be productive. So that's what I'm going to be talking about. So I would describe this talk as a potpourri category. So there are going to be a bunch of little bits of different things that I've picked up over the years. I've attended talks like this before, and I always really enjoy just hearing about how other people get their work done. Hopefully you can, pick up at least one thing, even if not all of the things apply to you. So the first thing I'd like to talk about is like a typical remote setup for me. So let's say I have a client, they're like, I don't know, a bank in Costa Rica or something like that. They have data about people applying for loans to buy houses in Costa Rica in a database. I'm in America, I'm in Los Angeles. Well, the typical way for me to get access to that data, to train a credit model, to give to the bank so that they can book their loans, looks something like this. So I'm on my laptop. I set up a VPN to their server closet or their cloud service or whatever. And they provide a development node for me, which I SSH to. SSH is the remote shell program. And from there, I can connect to their database using R in a database driver, something like that. So this is a little involved. And because of these kind of layers of security, like it can be a little more difficult to get things going. There's definitely a little bit of a learning curve to it. So I'm gonna just talk about a couple different things. So if you haven't ever seen what SSH looks like, it's just like this. It just runs in your terminal. Yeah, so the first thing I'm gonna talk about, and I'm thrilled that James just brought this up, is highlighting and colored output. So if you weren't aware of this, there is a package, Crayon. It's the de facto highlighting package. So let's go ahead and demo that real quick. So R vanilla, unknown option vanilla. is it dash vanilla?
Dash.
There we go. Cool. So is my font big enough? Can people see that? I feel like it's too small. I'm going to crank that up a little.
It's big enough.
Okay, cool. So, read CSV. Okay, so I'm just going to read in a CSV. Okay, so I got a CSV of like proteomics from a client. So let's go ahead and read that in, print it out. Cool. And so what we can see here is that there's like some coloring built in. So actually the readr package uses another package for making tibbles, and tibbles implements a method for printing out a summary, and it uses the crayon package in order to do this nice formatting for you. And so this is fantastic a lot of the time, but sometimes, like James was talking about, you want to pipe your output from R into another process, and these colors can actually mess that up. So yeah, so there's this PR I wrote a while back for implementing no color. No color isn't really a standard, I guess. It's like a convention. But anyway, you just set that as an environment variable on your command line. And then it should turn off all the color. We'll see. So let's see. What was it? Download proteomics. Color went away. So if you are piping this output into something else, there's no more colored control variables in there to mess you up. So that's one nice thing. So another thing is to mention with this architecture is, so Crayon is, it's an add-on package. If you want to use it, you have to kind of opt into it. So if you're using anything in like base R, so if we did a regular read.csv, you know, download proteomics. All right, so no coloring there. And so you say, well, you know, I want the color, but, you know, base R hasn't added all the crayon features. So there's another package out there called color out. Is it color out? There we go. So let's do that again. And now everything is colored. It's colored a little weird because of how it's implemented, which I find kind of amusing. So you can see like with the protein, it's like a green P and then a 1. Color out actually fiddles with the internals of R and checks each little token that goes on the output. And if it's a number, it makes it one color, text goes another color, and so on. But this kind of thing is very, very helpful. I actually have it load up by default. So if I start R, yeah, I already got it going. I got my Thursday, March 25th, 2/11, cool. Oh, and this is a server, so it's on UTC, so that's why it says it's tomorrow, just in case anyone's curious about that. Oh, another quick thing if you haven't seen that before. So you don't have to type out quit in order to quit R, just do a Control-D a couple times and it'll close it. I do that all the time. So yeah, that's those two things. That's all I wanted to mention about color. Next topic, graphics. So visualization is super important. You know, very often you want to do like box plots, histograms, scatter plots, whatever, as you're getting to know a data set, right? And you want to be able to have this really fast edit visualize cycle. And ggplot is great for this because it's kind of concatenative. You can kind of build up your plots as you go, right? And so obviously, if all you have to work with is this terminal, that can be a little challenging, right? So how do you get the graphics from the dev node to your computer? There's a couple different ways for that. So the traditional way of doing that would be what's called X11 forwarding. X11 is I don't even know how to describe it. I guess it's like a graphics device protocol that's network transparent, something like that. But anyway, if you have an X11 server on your computer, you can turn on forwarding over SSH by doing a -X right there. And then your plots will just pop up right away. This computer is a Chromebook, so I don't have that. But this is something I have used in the past. So if you don't have access to that, another good package you can try is using the server package, which I believe is by Yiwi. But basically, it's kind of like the R version of the Python simple HTTP server. Hello? Okay, cool. So it just starts a web server in the background in your current directory. And so if you're doing that, you can write a plot to disk and then open it up in a web browser. In order to do that, typically you need to have like a dynamic proxy, so SSH-D. This is another thing that like security conscious admins like to turn off, but it's also, like I say, a survival strategy. You can also use this to transfer files. So that's a nice trick. And the final one I'm going to talk about is this this package I've written, which is called OSC1337. And if the name doesn't give it away, like you shouldn't be using this for anything critical, but you know, sometimes it can be really handy. So let's just go ahead and take a look at what it does. So we're going to attach this package. It looks like nothing happens. Okay, let's go ahead and do a histogram. So anyone have a favorite data set? If not, I'm just going to do sleep. All right. Sleep $extra. So what's going to happen? Hey, there's our histogram directly in the terminal. So what's actually happening here? So this particular terminal is called HTerm. It is the terminal built into Chromebooks. And for a variety of reasons, it is implemented inside Chrome itself. So this terminal is in fact a web browser, and you know, the Google developer that wrote this has implemented some control code so that you can pass images directly from you know, the development node across SSH, and then you know, display it directly in this web browser. So this is a nice little thing. There's several other control codes in this package to do a couple different things. So there's this show command, which will do a plot. You also have a notify command, which is nice, and a put command. So those are implemented as terminal escapes. So that's there. This probably will never get to crayon until they come up with a way of setting the, you know, the color of text, the foreground color in a way that's acceptable to crayon policies, because most graphic devices only let you initialize with a background color. So fun trivia there. All right, so that's what I wanted to say about graphics when you're working on a dev box. Okay, so this is a little bit about editors. So if you're not familiar with the text editor, it's probably worth your time to learn one if you're going to be working on remote machines very much. So the ones that everyone always talks about are ESS and VimR. So that's for Emacs and Vim respectively. Those are both fantastic packages. You know, they're very customizable. You can do a lot with it. You know, I personally don't use them. What I do is a little bit different. I just use the screen program directly, and you can do a lot with screen. This talk isn't about it specifically, but I'll just go ahead and show you. So start it up. So screen lets you run multiple shell processes inside one terminal. So it's pretty handy. So I'll go ahead and start up R in one. So down here, we can see that R is running in position 0, and my shell is in position 1. Let's go ahead and start like tmp.r, something like that. So there's a little bit of customization you can do. So do I want it like that? So now I've got kind of my R on the right-hand side and my my editor on my left-hand side. I think I actually want it the other way around. So we'll do something like that. Okay, cool. So, you know, we might want to do like library. Anyone have a favorite library? So library LME4. So over here, I'm in temp.r. Cool. So then I have a shortcut key defined that sends it over to the R process. So you just hit Control Enter, and then it copy pastes the line that I'm on right over there. So this can be very, very useful if you're editing like some more complicated R scripts and you just you don't want to like be selecting stuff line by line doing that, especially when you're in screen, because as you can see, it doesn't respect the virtual division between these two things. So it's not, again, just to say it's good to know your editor, know your tools, and you can pretty directly integrate them with R and that kind of stuff using those common tools. So I think I got like 5 minutes left. I forget how much I have left. Oh, R profile. So this is the so-called dot file, your personal customization and configuration file for R. Dot files are definitely a thing. I've given an entire hour-long talk on them at the KLF conference. But I'm going to call out like two things specifically because I really feel like they should be in everyone. So the first one is this little snippet options with equals, and then we got a system command there, and set width on resize equals true. So if you're used to using R, it does word wrapping automatically, right? So if we print out sleep over here, we can see that we've got kind of two columns going on, or three columns. This one's not wide enough. Let's do empty cars. And you'll really see the word wrapping. Okay, so we got empty cars, and it is word wrapping this, and you know the window is so narrow that it can only print one thing at a time. Now, if we were to resize it, the set width option lets R dynamically pick that up by listening to the terminal's signal back to the process that it's resized. So let's go ahead and resize the terminal. We'll run the exact same thing. Bam, extra columns. We didn't have to configure this again. Like, I feel like this should be a built-in default, but it's not. So, oops, just wanted to call that one out. The second one that's extremely helpful in my experience is this utils : rc.settings ipick equals true. And this is kind of a deep pull from the manual. But this enables autocomplete for libraries. So you can do library L and then the tabs, and then it will list the different libraries based on that. I find this extremely helpful. It's not set as a default because it does have to check your library for which packages you have installed. And I guess that was not okay for the core R developers, but like I say, I really feel like this is a great default. It's worth adding to your own R profile. Let me pull up my own .R profile, see if there's anything else worth mentioning. Not really. I set a default repository, digits, that kind of stuff. Load up color out by default. Oh, I got some stuff to automatically set the version of R if I go into the screen browser. So you can do lots of stuff. You can set a default palette, print out a timestamp, all that kind of thing. There's a pair of functions that if you define in your R profile, they'll get called automatically when you start and end a session. So .first, .last. So you can use that to like automatically save your history and stuff like that. Pretty handy. All right, so talk about scripting just a little bit. So there are a lot of good packages for argument parsing. So argparse is a good one that James mentioned. Other ones I've used would be like docopt. It's also pretty good. I've written one myself. It's called Fuego. It's heavily inspired by Python Fire. It's a little less flexible than the Python version because our objects don't have vtables. So you can't go nuts with method chaining really like you can with Python, but it's there too. And the other thing I'd like to call out is Dirk Edebutel's little R package, which will make the command line interface a little more standard if you're doing a lot of like Unix scripting. Yeah, and that's about it. I'll just kind of recap all this. So most of my work is done through this this little keyhole through an SSH shell. on remote servers. You know, I often don't get to choose it. That's just the only thing you get. But like with a little bit of practice, you can be reasonably productive anyway. Yeah, so I think that's